Hello, scholars. Time to learn about bonding, chemical bonding. If you were James Bond fans, that was maybe funny. Alright, so chemical bonds. What are they? Here's just our definition for what a chemical bond is. It's an electromagnetic, so that means, positive and negative attracting each other, interaction between atoms that bind them together into larger structures. Because obviously everything's made of atoms, but they're bound together, because if they weren't bound together, it would just fall into a pile of dust. So what is it that binds everything together? And everything makes bonds except for the noble gases. The noble gases already have full electron shells, which is called the octet rule. And what we find is that everything wants to have full electron shells. Right, but if you draw the Bohr models for the noble gases, they all already have full shells. Okay, so we've got two types of elements, and I understand semimetals are also in here, but they can behave like either one. So we've got two main types of elements. So if you combine them together, you can get three different types of bonds. So if you have a nonmetal and a metal, you're going to get what's called an ionic bond. If you have two nonmetals, so I'll just do two arrows, bonding together, or the same nonmetal twice, you get what's called a covalent bond. And if you have two metals binding together, you get a metallic bond. Okay, so let's talk about two properties, melting point and conductivity, before we go in and we talk about the different types of bonding. So if I just use a particle explanation here, and let's say I've got a solid, there are some sort of forces binding these together. Right, so if I zoom in on this, there are forces, unseen, electromagnetic forces, that are connecting all of these particles together. Because if they weren't connected together, it would just disintegrate. It would have no structure. But if it's a solid, then we know that there's something holding it together. Okay, so let's annotate that. I'll say substances are held together by forces. So for me to take this solid and for me to melt it, what has to happen is I have to add energy in order to overcome these forces. So what does that mean? That means if I add a lot of energy, that means I have strong forces. Right? So if it takes me a lot of work to melt it until it's, completely just moving around, just kind of random, it doesn't really have a structure anymore, it's all melted, that means it took a lot of work. They were really strong forces. If it takes a little energy, it'll still look melted, it'll still be a liquid, but obviously it didn't take nearly as much effort. So melting point, which is the temperature that something melts, is actually a good measure of how strong these bonding forces are. A high melting point means really strong forces. Okay, what about conductivity? Well, we know conductivity is important because without it, we wouldn't have electricity. And so here's the question, like, what is electricity? Well, I'm just telling you here. Electricity is charge, which that means either positive or negative, in motion. So in the wires in your house, you have electrons in motion. Right? So anytime you have a substance that allows charges to move, that means it conducts. So let's just write that as a definition. A substance that allows charges, plus and minus, to move is said to conduct, or to be conductive. It exhibits conductivity. They're all related words. So let's go through and actually talk about the different types of bonding. So ionic bonds are a metal and a nonmetal. So let's take a very characteristic example of sodium chloride. Sodium chloride is actually table salt. It's an ionic compound. It doesn't look anything like sodium or anything like chlorine. Sodium's a metal. Chlorine is a yellow gas. Sodium chloride is a white crystal. Completely different, yet it's made of those two elements. So what happens is, if you draw, I'm going to draw Bohr models, but only the outside shell. So sodium has 1 valence electron. This is called a Lewis dot structure. Chlorine has 7 valence electrons, so I'm just drawing the valence electrons here. And if you keep in mind this octet rule, that everything wants to get a full shell, look how close chlorine is. It's very close. It just needs 1 more. And chlorine has a high electronegativity, whereas sodium has a low electronegativity. So if these two fight over sodium's electrons, sodium's going to lose. Chlorine's just a lot stronger. And so now you have chlorine with a full shell, except it has an extra electron, so it has a negative charge. And then sodium has lost an electron, so it has a positive charge. Now let's think about the octet rule for a second. If I draw the full Bohr model for sodium, okay, we have 8 electrons in that second shell. It's full, right? And then we have the third shell, which has 1 valence electron. Now I just took away the third shell, so let me delete that. Oops. So if I delete this, this is what the sodium plus looks like. And would you say that this has a full outer shell? Yeah, it does, because the outer shell is now its second shell, and I would describe that as full. Well, what happens when you have a positive and negative next to each other, right? We've got a positive, we've got a negative. They're going to attract each other. And so this attractive force is the bond. So this attraction equals the bond. Well, this is an extremely strong attraction. So the strongest, in fact, I would say. And so this has the highest melting point of the 3 types of bonds we're going to study. It forms a crystal lattice as the structure. A crystal lattice means it's a repeating pattern of positive and negative charges that just repeat forever. Now, here's a negative. What has to go on this side of the positive? Well, if I put a positive, they would repel each other. So this positive has to actually be surrounded by negatives. All right, so you get the idea. This is the repeating pattern. This is the crystal lattice. Quick vocab here. This positive charge has a name. It's called a cation, like cat, meow meow. Whoop, that didn't work. Cation. And this negative is called an anion. An ion is just a charged atom. Anion is a negative one, cation is a positive one. That's all vocab that you need to know. Okay, let's talk about conductivity. Well, we know our definition of conductivity that we just went over is we have to allow charge to move. Well, in this crystal lattice, these charges are locked in place. If I want to try to move it, I can't. It's locked in this crystal lattice. But I do have charges. So what happens is, if you either melt or dissolve the crystal lattice, so melt or dissolve, what happens is these positive and negatives can now move around. So I'm drawing arrows since they're moving around. So melted or dissolved, this will conduct. But as a solid, it will not conduct. Okay, so that's ionic in a nutshell. You'll have to read to cement it, of course, and you could rewatch the video on your own, perhaps. Covalent bonds, remember this is a nonmetal plus a nonmetal, and let's take an example like oxygen. Oxygen has 6 valence electrons. So again, I'm drawing a Lewis dot structure, which is just the outer shell. And these both have high electronegativity. And so I can't just have one oxygen take the electrons from the other one. And that wouldn't really work very well either, because let's say this one took these electrons. Well, now this one has an octet, but this one doesn't. So I'll go back. That's not going to work. So what we're going to do actually is we're going to share electrons. And so when they share electrons, the electrons go in between them. So I'm going to share these two and these two. And so what I have then is I have two oxygens. I have these electrons, which didn't do anything, which we call lone pairs. And then I have these 4 electrons in the middle. And so if you look at the electrons around each oxygen, this one, if you count all the shared one, has 2, 4, 6, 8. It has an octet. And so does this one. It's just these shared ones count for both. And a lot of times how you'll see this written is each one of these pairs will just be written as a dash. So a dash just means 2 electrons. This is how I'm going to write it. So don't be confused when I write it like that. This actually has the lowest melting point. So it has the lowest melting point, which means the weakest bonds of all of the types of bonds we're going to study. This structure where you have a certain number of atoms bound together with covalent bonds is called a molecule. Molecule structure. And a molecule is just a group of atoms covalently bonded. Now, how's this different than an ionic crystal? Well, it's a group of a certain number. I'll add that, certain number of atoms. Whereas the ionic crystal is just going to go on forever, right? This structure could repeat forever. This molecule, that's it. And so oxygen, here we would write it as the molecule O2, because there are 2 O's, and that's it. It's an insulator because these electrons in here cannot move. So insulator means it does not conduct. So it does not conduct because electrons cannot move. They're locked in place. What about metallic bonds? So let's just say sodium and sodium. Well, these both have really low electronegativity. And so in order to get their full shells, they just need to get rid of this one electron. So what they do actually is they just kick it out. And so what you get left with is a field of cations. Remember, positive charge is a cation. I'll just do 6 because I'm running out of time here. And then you have this sea of electrons, which is in constant motion. So I'm just going to draw it randomly. But what I need you to understand is that these electrons are actually constantly moving around because none of the atoms have a high enough electronegativity to capture them. And so we can call this a metallic solid or a malleable solid because it can easily move, because what's holding this cation in here is this sea of electrons. So if I move it here, are these electrons still moving around it? Yeah, so it's still kind of attracted. And will metals conduct electricity? Absolutely, because these electrons are able to move around, and these electrons have a charge. Let's see. We'll do a couple sample problems until I hit my 15-minute mark. How could you tell the type of bonding present in an unknown sample? Well, you could do a couple things, right? You could look at melting point, because we know ionic have high, covalent have low, metallic are kind of in the middle. You could look at conductivity. You could see if it's malleable. What else could you do? You could look at the phase. If it's ionic, it's going to be a solid always. Covalent is more likely to be a liquid or a gas, although it could also be a liquid or a solid, but it could also be, no, I said it right the first time. All right.